Number 1 asks you to write each quadratic expression in standard form, and you can draw a diagram if needed. So the diagram method is that you think about it as doing area. So you have this piece is x, this piece is 4, then you draw it again, and you think of this as being x and -1, and you create these rectangles. It's also called the area model because you're looking at doing the area of each of these little rectangles created. So in this first box, the area would be x times x, which would be x squared. In this one, it would be x times -1, so that would be -1x. In the bottom one, we have a 4 by x, because this length right here is x. So 4 times x is just 4x. And then this one would be 4 times -1, which would just be -4. And then you have some like terms here where we have this is -1x and 4x can add together. So these ones add together to be positive 3x. So then your overall polynomial is x squared plus 3x minus 4. So you just add all of those areas together. So that's the area method. You can also do distributive property where you distribute the x to the x. We're going to take the x and multiply it in. And we're going to multiply it to both terms because we need to distribute it to both terms. So then x times -1 is -1x. Then we're going to distribute the 4 to both terms in that next binomial. So 4 times x is 4x, and 4 times -1 is -4. And then again, you end up with these like terms of -1 and 4x, which add to that middle term. So either method is totally fine. I'm going to just do the distributive property here. So I'm going to take 2x times 3x, which gives me 6x squared. Then I'm going to take 2x times -1, which gives me -2x. And then -1 times 3x, which is -3x. And then -1 times -1, which is +1. And then I will add these middle terms together that are like terms, the -2x and the -3x. So we have 6x squared minus 5x plus 1. Number 2, consider the expression 8 minus 6x plus x squared is the expression in standard form. So remember, standard form means that you need to have the highest exponent of the x first. So when we're talking about quadratics, that's your x squared term needs to come first. So I'm just going to say a in general. So ax squared, then any x terms that you have, so plus bx, plus any constants that you have that don't have variables. So we need the x squared, then the x, then the constants. And so that is not true here. Okay, no, because the x squared term isn't first. And the constant isn't last either. So if we were going to write it in standard form, it would be x squared, the -6x in the middle, and then the positive 8 at the end. Then they ask, is it equivalent to this binomial squared? And so we can multiply this out to check. And so when we multiply this, we know when we multiply the x times the x, we're going to get x squared, right? We also know that when we do -4 times -2, we're going to get +8. That's that end term. Then you're going to get these middle terms when you do the x times the -2 and the -4 times the x. So I'm just still doing that distributive property, but just looking at it a little bit differently because I know I'm going to get this -2x and this -4x as my middle terms that are going to add together. And so then we end up with x squared minus 6x and then that plus 8. So yes, it's the same thing. So yes. Okay. And so you could, you can start to get a little bit faster at these binomials squared. If you can remember, like we're going to get an x squared, we're going to get a positive 8 when we multiply those together. And then we just need to figure out what the middle term is going to be. And that's going to be when we multiply the x with the number. So negative 2x and negative 4x gets us that negative 6x. Number 3, which quadratic expression is in standard form, right? Which is that ax squared plus bx plus c. And if any of them are missing, that's fine. We could have a 0 in there somewhere. So none of them that are factored are in standard form. Okay, so anything that's factored for sure is not in standard form. And that ruled out everything except for c in this case. And we also see that it has our x squared term, then our x term, then our constant. So C would be the standard form. Number 4, explain why 3x squared can be said to be in both standard form and factored form. So it's only one term. Okay, so it's one term. So that means it can't be factored any further. Okay, there aren't going to be any common factors if there's only one term. It's also called a monomial. And then it also, because it's only one term, has the x squared term first. And so if we think about standard form, it would be like this: 3x squared, we have 0 x's and we have 0 constants. So those we wouldn't need to write, and we would just have that 3x squared. So it can't be factored any further, and it has the x squared term first. Number 5, Jada dropped her sunglasses from a bridge over the river. Which equation could represent the distance y, that it's fallen in feet as a function of time t in seconds? So remember, you've got kind of two things going on here, right? So we've got this like bridge, right? So obviously I'm not an artist, but we've got this bridge, and then she's going to drop a pair of sunglasses, okay, off the bridge. So we've got these sunglasses that she's going to drop. So now the sunglasses are going to be traveling downward, right? They're going to fall. And after each second, this distance that they've traveled is going to get more and more per second, okay, because of gravity. So we've got this happening. And as those sunglasses are dropping, we're measuring that distance, okay? So how far is this distance? Okay, so at 0, it hadn't fallen at all. Okay, and then after a second, it's some distance. After 2 seconds, it's more distance, right? More of a gap. And after 3, it's even more. But then that distance is going to be a positive number, okay, even though it's going down, okay, but the distance that the sunglasses has traveled is positive. And the reason that's important is we don't want it to be this negative downward motion. Okay, we don't want to have a negative amount. We're not losing any distance. We're actually gaining distance. And then we also know that it has to be a quadratic because it's not falling at a constant rate. So the quadratic means that we were down to either A or C, and the fact that it's positive distance leaves us with our only option of A. Number 6, a football player throws a football. The function h given by 6 plus 75t minus 16t squared describes the football's height in feet t seconds after it's thrown. Select all statements that are true about this situation. So A and B talk about where the football was thrown from. A says it's thrown from ground level, and B says it's 6 feet off the ground. So only one of these can be right. So remember that this happens at 0 seconds. So if we plug in 0 into here, okay, these both go away because multiplying by 0 is 0. So that's why this 6 is your initial height. Okay, so your initial height is the constant in the function. So that means that B is correct. In the function, negative 16t squared represents the effect of gravity. We know that to be true. Okay, that t squared variable is from gravity. The outputs, h, decrease and then increase in value. Well, we know that this is going to be an upside down parabola, right? So we know it's going to look something like this. It's going to start at 6 feet. It's going to go up and then it's going to come back down. So we know that this is false. Okay, the outputs are not going to decrease and then increase. The function has two zeros that make sense in this situation. So it's true that it has two zeros. One is here and one is here. But this one is going to be negative time, which does not make sense. Okay, the football, we're not going to say that it's traveling backwards because we're not going backwards in time. So only one would make sense here. And then it says in F that the vertex of the graph gives the maximum height of the football. So here would be your vertex. And if you went over to here, it would in fact give you the maximum height. Okay, that would be your t value, or sorry, your h value. So you'd have some time when it would happen. And then this output, h of t, would be your maximum height. Number 7, two rocks are launched straight up in the air. Rock A is given by this function, and rock B is given by this function. In both functions, time is measured in seconds and height is measured in feet. Use graphing technology to graph both equations. So I've done that here. So f of x is the red one and g of x is the blue one. So the f function is rock A, right? And then rock B is the blue one. So what is the max height of each rock? So for rock A, the max height is here. So 18.63. Or 18.063 actually. So I'll just say 18.1 feet. And then rock B is at 11.25 feet. So 11.25 feet. Which rock reaches its maximum height first? So remember that the x value is how long it took to get there. Okay, so rock B only took 0.62 seconds to get there, where rock A took 0.9375 seconds. So it would be rock B reached first. And you could say because the time is less, right? So the 0.625 is less than 0.9375. Or you can say that it occurs further to the left on the graph, right? So if you want to talk about position on the graph, it happens further to the left, which means that the x value is smaller, or in this case, the t value. Number 8, the graph shows the number of grams of a radioactive substance in a sample set at different times after the sample was first analyzed. What is the average rate of change for the substance during the 10-year period? So this means that you want to subtract the values. Okay, so we want to look at the height value here. So this is about 6, and it started at about 30. So we want to subtract those to look at the actual change in the 10 years. And then we want to divide by the number of intervals we have, which is 10 for the years. So subtract those y values and then divide by 10. So we get negative 24 over 10, which is negative 2.4. And then what are they measuring in years? Grams per year. So grams per year. And then is the average rate of change a good measure for this? So what I kind of like to do is connect the two values. So we were doing this point to this point, and I just connect those with a straight line because that's what this gives. Okay, average rate of change gives the constant change. So that gives you kind of like if it were linear from start to finish. So this is a constant negative 2.4 grams per year change. So in this case, it doesn't, because most of these dots are not on the line. So no, because the data doesn't graph linear. Okay, or the dots aren't on the line, the dots don't make a straight line, something like that. Number 9, each day after an outbreak of a new strain of the flu virus, a public health scientist receives a report of the number of new cases of flu reported by area hospitals. Would a linear or exponential model be more appropriate for this data? So remember, for linear, that means that at equal increases of your days, that your flu cases should have equal increases or decreases also. So when we're looking at linear, we're looking at how much do we add or subtract by. So in this case, we add 8. Here we add 10. Here we add 16, 21, and 30, right? So linear, no. Okay, not a constant difference, which means in this case, not constant adding. It could be adding or subtracting. In this case, it was going up, but it's not adding or subtracting by the same number. So then for exponential, you need a common rate, okay, or a common multiple. So in this case, you would do 28 divided by 20 to see if that ratio is the same. So 28 divided by 20 is 1.4. 38 divided by 28 is 1.35. 54 divided by 38 gives us 1.42. 75 divided by 54 gives us 1.389 or 1.39. And 105 divided by 75 gives us 1.4. So we had 1.4, 1.35, 1.42, 1.39, and 1.4. So it's not exactly exponential, but when you're using data, it's never going to be exact, but it is closer than this change in the differences. So I would say yes to exponential. I would say exponential is more appropriate. Whoops. Because the growth factor is very close to 1.4 for each case, right? So not exact, but they're all pretty close to 1.4 when you divide those. Then number 10 says that A of T is the average high temperature for Aspen, Colorado, T months after the start of the year. M of T is the temperature in Minneapolis, Minnesota, which is actually where I am, T months after the start of the year. Temperature is measured in degrees Fahrenheit. So what does A of 8 mean in this situation? So A means that we're in Aspen, right? So the A is Aspen, and then 8 is the month. So this is the temperature, or the average temperature, right? So this is average temperature in Aspen in August, which if we look at this graph is about 75 degrees. Then which city had a higher average temperature in February? So February is the second month. So Minnesota is down below 30 degrees and Aspen is almost 40 degrees. So Aspen has a higher average temperature in February. And then were the two cities' average high temperatures ever the same? And if so, when? So we see that they're the same when they cross here. So they cross between month 3 and 4. So I would say that's mid-March. And then again between month 9 and 10. So that would be mid-September.